Okay, so good evening, all of you. Welcome to this fifth session of NPTEL problem solving sessions on engineering meteorology. Uh, we shall go ahead with the last discussions that we did. So, okay, so let us begin our discussion today from where we ended last time. We have seen that there is a technology called as transducers, which is used to extensively in measurements in rather we should say digital measurements, which are purely different from the complete mechanical measurements that we used to do. And we had seen that transducer is a device that can convert physical quantities into electrical signals and vice versa. This means that if we have a physical quantity and we subject it to the transducer will be capable of converting it to a voltage or current. And whenever I say current, we typically mean a voltage rather than, and here we have any physical quantity. Now, this transformation is possible and this transformation is possible too. So, we have seen last time that if we supply voltage, we can see the change in physical dimensions of the body. Now, let us start our conversation from here today. So, this essentially, when we see and if we consider this to be the heart of a transducer, we typically are doing here is energy convergence. Right, if we have here say pressure and pressure is converted into a voltage, then we are typically converting force or say pressure is nothing but force per unit area. So this is force, and this force is say mass into acceleration as per Newton's law, and this acceleration again is a double derivative of double acceleration of speed or velocity. So we are typically going from a moving particle, and that energy that this particle is going through while moving, this energy of movement is converted into a voltage signal. Similarly, if we say that there is a container in which water is boiling, now if this boiling water temperature I want to measure, this temperature I can measure in terms of voltage. And again, what I am doing is I am converting this thermal energy, into electrical voltages. So we are doing nothing but energy convergence. So let us first, in a structured manner, see in a transducer what are different types of energy transformations. So we have seen that we are converting some form of energy into another form of energy, and that one typical form, either from or to, should be the electrical form. Fine. So let us begin with this, that the first type of energy transformation we see is the electrochemical energy transformation. Now what it does is this, as the name suggests, there is some sort of chemical reaction that is being converted to or from into electrical energy. Now, if we want to see a typical example of this electrochemical energy transformation, we can see we have batteries wherein we have a positive and a negative terminal and some sort of reactions going on here, and this potential we get. But this specifically is not a transducer. This is just a case I showed you of chemical reaction. Now, if we typically want to say that we want to design a transducer wherein the transformation is being done from chemical energy into electrical energy, can you think of a very generic experiment, or say a very daily day-to-day life transformation that we see wherein the chemical energy is being converted into electrical energies? You should think of it as a home assignment wherein uh, the work is to identify a daily routine process in which electrochemical energy transformation is being done. So this shall be your takeaway assignment, and you should observe your vicinity wherein you can find such a thing being done. I'm extremely sorry. I think I didn't present my screen. Okay. Now is it visible?
Yes, sir.
Okay.
Yes.
You should have pointed me out earlier. Anyways, so what we did was, I shall show you that typically what we are doing is we are doing energy conversions, and in the energy conversion, the first energy conversion that we saw is electrochemical energy conversion. Now the second form of this energy conversion from a physical property to electrical energy is electromagnetic energy conversion. So we have extensively heard about EM waves, and we know about EM theories also, in which we say that uh, electrical or rather electric field and magnetic field go side by side, wherein we said that if there is a pipe of this sort and these kinds of electrical fields are there, then it is very obvious that we will have a magnetic field also around this electric field. And why does this happens? Because say if this is the direction of the field and there is electric field is E is equals to, say, let us not write the formula per se, so E is proportional to the charge that is being flown. Rest other things we have ignored, so there is area, there is the distance and everything, but typically this electric field is dependent on the charge that is flowing, and the flowing charge creates electric field, and this dynamic electric field creates a magnetic field B. So anyhow, when we see a system, we have seen Lenz's law, wherein we found the direction of current flow, and several other theorems which justify the fact that in case you have a dynamic electric field, you are obvious that you will have a magnetic field in that surrounding region. So these kind of electromagnetic energy convergence are very common while designing the transducers. Now the next kind of conversion we see is the electromechanical energy conversion. Now what happens here is you have a electric system, and when I say electric system, it is basically both at the micro and macro levels. That is, we are having currents also, and we are having charges also. So whenever we have such a system, and such a system is subjected to some sort of monitoring, it creates physical movements or deformations mechanically. And such energy conversion, if employed in designing transducers, it will be called as electromechanical energy conversion. A normal example of electromechanical energy conversion can be the electrical machines, such as the motor and the generator. Now here, if you put an initial force, mechanical force, it starts giving electrical power as output. And also in this example, if you give electrical power as input, it will give you mechanical rotation. Fine. So these kind of systems are well seen and understood in our day-to-day life and society, wherein the electrical energy and mechanical energy are interchanged and converted. So the next form of energy that we will see here is electroacoustic. Now what is this? Say we have a transducer in which, when we apply a electrical signal, subjected under monitoring, what it does is it creates vibrations, or as we commonly understand as sound. So these kind of energy transformations will be called as electroacoustic energy transformation. Another type of this transformation is photoelectric energy transformation. Now what happens here is, we have some form of electrical energy here, and we are converting it into light related properties. So what it can do is, just in case of a photodiode, once this stimulation is provided, what it does is it starts to emit light. So these kind of transformations are photoelectric energy transformation, wherein this photo means light energy. So what we are typically doing is we are creating light or light related properties. Fine. The next kind of energy transformation that is very common, and the last possibly, is the thermoelectric energy transformation. So in this, what we do is, with this transducer, we apply electric signal, and what we get here is thermal energy or heat. So there is one thing very important that we can point out here is, say there is a conversion we have electric properties here, current or charges, and we are able to create, say, mechanical movement. So it is typically of the class of electromechanical energy conversion. Now this mechanical energy conversion in itself can create magnetic effects also. It can create thermal effects also. It can create optical effects also. It can create chemical effects also. So all kinds, and optical we did, right? Yes, optical we did. So also it can create acoustic effects, because this mechanical motion can create, see, if you are, this is a box and you push it, and it hits a wall, so it will raise the temperature of the wall, it will create vibrations in the wall, and also with different other parameters. When you hit a uh, electron in a cathode ray tube, it creates optical effects, scintillations, kind of things. So this mechanical movement in itself can create all the secondary effects that we have discussed here. But there are specific cases where we need the transformation of electrical energy into, say, acoustic energy first hand. We do not want a subsystem or sublay in between. Why? Because, see, we are not interested in energy conversion. Our aim here is to model or portray or write in form of equations or contain information about a parameter accurately. We did in the first class what is accuracy. So our aim is to see how are we going in this channel. First we used to did mechanical do mechanical conversion, these mechanical instruments, but these mechanical instruments have certain errors and uh, problems of dynamics, wherein we shifted to electrical measuring systems. And when we moved on to it, we found that these transformations are good because we can find the relations in terms of voltages and current, and measuring those voltages and currents is easier for us, and based on those voltages and currents we can easily convey the information about the parameter without any error. So this accuracy is very important to us. And since we have seen that all these transducers are typically doing energy conversions, and from the universal law of energy conservation, we know that energy is neither created nor destroyed, but it is converted from one form to another with subsequent losses. Now, what does this mean? This is a very important parameter here. Whenever we are talking about designing transducers, it is very essential for us that we do not go on to rely on secondary transformations. And what I mean by this saying here is, say we have a mechanical movement, and from that mechanical movement we are getting electrical outputs. This is fine for us. But if we go vice versa, and from electrical to mechanical we get an output, and from that mechanical output we want to create a acoustic output, what will happen is some energy is lost here at this point, say EL1, and some energy is lost in conversion of this EL2. So what typically this E was proportional to M. Now what happens is this M suffers a loss of EL1 and EL2. So this, if say, is M dash, and now we are getting E proportional to M dash. So ideally what we should have got is this, and the result that we actually get is this. So if we want to plot this result in terms of a graph, say this is the electrical property and this is the mechanical property, and suppose this is the kind of graph we would have got in an ideal condition. This was the relation between the electrical and mechanical transformation we would have got. We typically end up somewhere here. With this delta V or delta E kind of an error that corresponds to EL1 and EL2. So every time we do energy conversion, we suffer the loss at one instance. So this is not advisable at all that we try to use this mechanical subset as a part of our transducer system, wherein we are creating secondary effects with the help of this primary mechanical shift that we have got. Hence, it is important for us to understand that if there are systems wherein we want acoustic outputs, we want chemical outputs, or from chemical outputs we want electrical outputs, it is very essential for us to design the systems that at first hand can give you the results. So this is the crux about the energy conversion involved while designing the transducers. Now let us move towards the important step, that is the principles of energy conversion that govern design of transducers. So in the types of energy transformation, we have seen that there are different trans different methods of converting the electrical signal into different parameters. Now we will continue with this in a short while. So let us go ahead with this discussion on principles of energy conversion. So the first principle of energy conversion that we will see here is the capacitive rule. Now we all know about a parallel plate capacitor. So what it does is, say we have two metal plates, and on these two metal plates in between there is nothing but air is filled, and this distance is d. And by electrostatic properties, if we create charges on these two plates, so what it does typically is, in between this there is a electric field generated, and that electric field is proportional to the voltage that is being generated between these two plates, and this voltage in turn is dependent on the inherent property that is called as the capacitance of this plate C. And we know that Q is equals to CB, wherein Q is the charge accumulated, C is the capacitance, and V is the potential difference between the two plates. Now, if we model this voltage between the two plates, we can say that this voltage V is electric field E into the distance d, and we can write this over here and relate this entire conversion, wherein we are converting the electrical energy or the electric field into potential V in respect of the capacitance C. So many a times when you design transducers, you have to know the concept of capacitances and capacitive transducers. And the very common example of such transducers are the touch screen sensors. So these touch screen sensors of your mobile phones are nothing but capacitive transducers, wherein the charges from the motion of fingers are used to drive the system. So say this is your mobile phone screen, and the glass you see here, there is a capacitive touch screen, and every time you put your thumb here, what it does is some charges, not just electron but let's say Q, some Q starts flowing here because of your thumb, and this Q increases the potential V by the rule this, and as soon as the potential of a specific point is increased, that specific button that you have created here is pressed. So this is nothing but capacitive generation of energy, and a live example that we saw. Now the next very common form of energy conversion which we glanced up upon in the last time also is a piezoelectric crystal. So basically it is this kind of a system, and let's say this is a quartz crystal. So this quartz crystal has its own inherent property of oscillations. And every time these vibrations or oscillations occur, so these vibration, what they do is, if between 2 points there is a vibration, because of this vibration some sort of mechanical movements are created. These mechanical movements are then converted into electrical properties. So we saw last time also in the case of microphones that if you have this kind of a microphone and you put a piezoelectric crystal over here, so every time you put in sound waves, the sound waves are converted into electrical pulses, which then are passed through an amplifier and then to the speaker. So this typically is the transducer or the principle of energy conversion, and this is the input, this is the output, this is the intermediate circuitry, and this is the final stage. This typically forms a instrumentation system. Now the next type of conversion that we need to see here is photovoltaic effects. So in the photovoltaic effects, like we saw previously also, say there is a active substrate here, and when I say active substrate, I mean and when I say active substrate, I typically what I mean is a conducting substance which is ready to give active outputs or give just outputs when subjected to light source under monitored condition or under given conditions. So say there is a light that is falling here, and this light source is nothing but electromagnetic waves. And with this, they create a lot of things here. First is the mechanical hit at the micro level, then they rise the temperature of this substrate, and because of these two combined effects, the electrons here are going to an excited state, and once this excited states of electrons is achieved at a considerable level and electrons starts to emit out, what we find here is a sustained electrical output. So with light, we could get currents or voltages, and if we reverse this effects from currents, we would get light. So in the reverse case, what would happen is, say this is my substrate, and from this I say it is the positive terminal, it is the negative terminal, and I apply a current here. The substrate, when activated through this current, would start emitting light. So we would have light. This is what is the concepts of LEDs, the light emitting diodes. Or the photodiodes. Fine. So till now we have seen the different forms of energy conversion, different methods or principles of energy conversion through which the transducers are designed and understood well. Now let us move on to understanding exactly how the transducers are designed. So we will see different types of transducers now. And the first classification that I will do here is, which I think I brushed up in the last